Let's take a look at the electric field in the neighborhood of an infinite plate with negative charge uniformly distributed on the plane. The magnitude of this electric field should be a constant number, as we have seen before, and it is equal to eta, the surface charge density, divided by 2 times epsilon 0. This magnitude is the same at one point or another point. Every point in space surrounding an infinite plane of charge has the same magnitude of the electric field. Now the direction of that electric field is perpendicular to the plane and pointing, if it is negatively charged, pointing towards the plane, and the same at every point. Same direction, same magnitude. If you move a little further away from the plane, if we're talking about an infinite plane, then the magnitude of those vectors, we should draw them with the same magnitude as before, and the direction continues to be pointing towards the negative plane. Now, under the infinite plane, the electric field will have the same magnitude as before, eta divided by 2 epsilon 0, and again it should point towards the infinite plane. So that means that the vectors underneath the plane point upwards, whereas the electric field vectors above the plane point downwards. We have a similar situation for a positively charged infinite plane. In this case, the electric field, well, the magnitude, we know it's eta divided by 2 epsilon 0, and the direction should be pointing away from the infinite plane, and it should be perpendicular. Every electric field vector should be perpendicular to the plane. Underneath the positively charged plane, situation is the same in terms of magnitude, but now the direction is the electric field lines, the electric field vectors point away from the infinite plane. Now let's see what would happen if we put two infinite planes, one positive, one negative, next to each other. Let's say that the positively charged plane is on top and the negatively charged plane is at the bottom. We're trying to find the net electric field in all the regions surrounding these two plates. Let's start by evaluating the electric field produced by the negatively charged plane. These are the blue vectors that you see there. On top of the negatively charged plane, the electric field points towards the negative plane. So all those vectors have the same magnitude and they point downwards towards the negative plane. Underneath that plane, the vectors have the same magnitude and they point upwards because they point towards the negatively charged plane. Now for the positively charged plane, we're going to draw the vectors in red. Those on top of the plane, positively charged plane, those vectors point upwards. Underneath that plane, those vectors point downwards. Everywhere underneath the positively charged plane, the electric field vectors, in red, point downwards, away from the positively charged plane. Since the electric field satisfies the superposition principle, we know that the net electric field is going to be the sum of those vectors, the blue vector and the red vector at every location. Notice that between the plates, the two vectors point in the same direction. So the net electric field is the sum of the electric field produced by the positive plane and the electric field of the negative plane. The positive plane has a density of charge eta plus eta, the negative one has a minus eta density of charge. So the magnitude of the electric field produced by the positive plate is eta divided by 2 epsilon 0, and the magnitude of the electric field produced by the negative plate is also eta divided by 2 epsilon 0. We're assuming that the two plates are identical in shape and have the same charge, same density of charge in magnitude, but one is positive, the other one's negative. So when you add those two numbers, you see that the net electric field between the plates is eta divided by epsilon 0, not divided by 2 epsilon 0, but by epsilon 0. The situation above and below the plates is different because in those regions the electric fields of the positive and negative plate are opposite in direction, which means that they cancel out each other. So the electric field is 0 everywhere except between the plates. This device with two plates charged, one positive, one negative, same magnitude, is called a capacitor. And it has the property that the electric field between the two plates is constant and equal to eta divided by epsilon 0, and it is 0 everywhere else. Now I want you to think about the following problem. We have 4 sheets, infinite sheets of charge, and 2 of them have a net charge that is positive, let's say plus Q, and these are the 2 in red, and the 2 infinite sheets in black are going to have a negative charge. All of these planes have the same net charge but different sign. Now, what is the electric field in different regions in space? Let's call those regions region number 1 to the left of the first one, number 2 between the two positive plates, number 3 in the middle, number 4 between the two negatively charged plates, and number 5 to the right of the last negatively charged plate. I want you to figure out how much is the electric field in region 1, 2, 3, 4, and 5, and to write your answer in each one of these regions as a constant C multiplied by E, where E is the electric field produced by one of these infinite sheets of charge. So that is E is equal to eta divided by 2 epsilon 0. So the options are A says that the electric field in region 1 is positive 2, so that means 2 times eta divided by 2 epsilon 0. In region 2, option A says that the electric field should be 4 times eta divided by 2 epsilon 0, and so on. In option C, we have a minus sign for the first electric field in region 1. That means that you think that in that region the field should point to the left. That's why the minus sign. So those are the options. Think about it, and when you have an answer, go to OutSpace and select your answer there.